I'm back again, ready to teach you some more about heat and energy. I know you've not had enough yet. So we will go into part 2. There are some little overlaps. It's not always so easy to teach things linearly. It's actually two-dimensional or three-dimensional. So please excuse when we go a little bit back and forth in the subject matter. But these are the topics we will discuss today, and very closely related to our previous lecture. The types of energy changes, chemical energy into different forms of energy, electromagnetic, photo, radiation, thermal. Thermal is heat energy, as we know, electrical energy, and it can also go in the other direction. So the sum of all energy is zero. That's the energy conservation law. It only changes its nature or its phase. It's all energy, just like we have the conservation law of mass. Mass is not destroyed or produced during a regular chemical change. Nuclear changes is something different. That is another story. And then we talk about the heats. We talk about heat of fusion, heat of vaporization, heat of condensation, etc., or heat of solvation. So I'll go a little bit into that, although these topics will also be discussed when one talks about liquids or solids, etc. So there's some overlap, of course. It can't be prevented. Here we have a wonderful old picture of an alchemist who, in his nice romantic laboratory, produced some chemical reaction that produces light, or a chemical reaction that produces light as an exothermic form of energy production. We should rather say exergonic. So the energy is delivered in the form of electromagnetic radiation. Chemiluminescence, we could call that as well. Like today we talk about the luminol reaction. So I don't know exactly what this man discovered, but it's certainly very exciting, and he is in awe. The people in the background sort of have a little nonchalant type of expression. They've probably seen this a few times already. So you see, energy can be converted, and there are many manifestations of different energy forms. We will look now into the heating curve when we do a physical state change. For instance, if we melt a solid, let's say we have a solid substance that is solid at room temperature, not a gas or a liquid to begin with, but a solid, and we introduce heat into the system, the solid material, then the heat will be absorbed. That means the kinetic movement of the individual building blocks of the crystal lattice will accelerate. The building block will sort of move around. I hope I don't make you seasick, but that's what you have to sort of imagine. And then there comes a time where all the so-called intermolecular forces are affected by the pumped in heat energy. And the intermolecular forces are the ones that keep the particles together in the solid manifestation, the solid state. So when the energy has reached that point where it can sever the intermolecular forces, then somehow the heat content of the system doesn't increase, because the heat is used up for snipping the intermolecular forces of the material. Once the last intermolecular force is broken, we have a total liquid state. So we're in a new physical state. Then, when we keep on heating, the heat will be absorbed as usual, changing the kinetic energy state of the individual particles, as we can see here in the rising curve, or the line with the inclination angle. So it's a rising relationship. And then we come to the second plateau, where even though we pump in heat into the system, the temperature does not change. These intervals that I've just been referring to, when we cut the intermolecular forces to the very last one, that energy is consumed for cutting intermolecular forces, as already mentioned, and that means the temperature doesn't rise at that point. So the heat content does not increase for the system. It is used up, the energy is used up for other things. When we are finished with the intermolecular force breakage, so to speak, then the body of matter can increase its kinetic molecular energy until it comes to the next plateau, which would be then boiling. So another state change occurs until the very last intermolecular force, which keeps the particles together in the liquid phase. Once the last bond is broken here, then we go into the gaseous state, and the energy pumped into the system will manifest itself as a temperature increase. So once we have a state change, the temperature remains constant for that interval. When the state change is complete, then the temperature rises as usual, as we would expect. Now these heats that are involved with the severing of the intermolecular forces, this heat is called latent heat. It's a hidden type of heat because it's not expressed in temperature changes or a degree rise in temperature. Now, as you go up the curve, you go from solid to liquid to gas, but you can also go the other way around. You can go from gas to liquid to solid again. So this curve works both ways. So when we go up the curve, up the staircase, so to speak, it's an endothermic process. So that means we have to absorb heat to do this. But when we go the other way around, or down the staircase, then it's an exothermic process. That means heat is given off to the environment. When we go from gas to liquid, we call that condensation. So the heat is called the heat of condensation. And as we go from the liquid to solid, you all know that that is freezing. By the way, melting point and freezing point is the same temperature, and boiling point and condensation point is also an equivalent temperature. So during a phase transition, the temperature remains constant. Now heat change is expressed usually in kilojoules per mole. And we distinguish between the molar heat of fusion, which is the heat necessary to melt 1 mole of substance, of solid material, or reversely, to freeze 1 mole of liquid of the same chemical. We also have the molar heat of crystallization, which is the change in heat from solid to liquid, or the heat content of the solid minus the heat of the liquid would be the change in heat, which we call crystallization. So notice that we can never really determine the actual internal energy, but we can only measure the changes in energy. So delta always means the change of. So the heat of crystallization is the difference in heat contents of the solid and the liquid, and the heat of fusion is the difference in heat content of the liquid and the solid. So the molar heat of crystallization is the heat needed to convert a liquid into a solid. So it's actually the reverse of fusion. Fusion means sort of melting. So it's the same energy content. As I already mentioned, vaporization and condensation is also the same heat change, involves the same heat change. So molar heat of vaporization is the energy required to convert 1 mole of liquid into 1 mole of gas. And remember, the temperature is always constant at this change due to the latent heat, as we already talked about. The molar heat of condensation is exactly the reverse. So the quantity of the energy is the same, only the sign of the number is different. So one is exo, one is endothermic. Now, as we talked about in our earlier episode, we need to measure heat changes in the laboratory, otherwise we have no data with which we can work and with which we can see how nature operates. But before we go to the calorimeter, I'd like to point out the heat of fusion and the heat of crystallization, the heat of vaporization, etc. Here we have those little styrofoam packing material segments. And let's say we have a solid, which is a regular alignment of the building blocks, very regular organization. It's a crystalline solid, not an amorphous solid, meaning it has internal structure and it's not randomly organized. And here's our Bunsen burner or any kind of heat source that will pump in heat into the system. Now these little individual building blocks are connected by intermolecular forces. These are so-called weak forces. So they keep sort of the particles aligned together. So they are all over the place. So everything is connected to its neighbor. But these intermolecular forces are very regular. So they're very, they have the same energy, so to speak, and the same strength of holding the individual building blocks together. So at first, when I heat up the system, the particles move around according to the kinetic molecular theory as you have studied so far and know how to apply. Now, pretty soon the energy will come where the intermolecular forces are broken. So that means the energy is not used for further agitation of the particles within the crystal lattice, but it's used to snip the forces so that we can now be in the liquid phase. Now normally in the liquid phase the particles have more freedom to move around, but there's still intermolecular forces involved. Let's say these intermolecular forces are now the yellow lines. So they're a little different. So they're between each of the individual building blocks. So when I pump in heat, the particles will move around, the energy state increases, but then we come to the second latent heat, which means the intermolecular forces are now being cut in half, broken up, and then eventually the particles will be in the gaseous phase. And you know what the gaseous phase is again. The particles have maximum distance between each other. Intermolecular forces are very weak. So that is the end of the story. That means we've reached the third physical state. If we pump in more heat, or you know what happens, the particles will move faster and faster, but there's no other phase transition. Now if we go backwards and we remove heat, cool the system, then the particles will come closer together again, intermolecular forces will come into play, and eventually we go back to the liquid and back to the solid. So we're going the opposite way. So when the particles come close together again, the intermolecular forces are back in action. So now we want to look at calorimetry once more. So a calorimeter is a device, either a primitive type like the styrofoam cup or a very sophisticated device. By the way, a Dewar or a thermos bottle would be somewhere in between. It would be a little bit more technically advanced than the simple styrofoam cup. But it has to be usually a device that does not allow any heat exchange between environment and the contents of the calorimeter. But we also have other types of calorimeters which are not at all supposed to be insulating. They are supposed to transfer the heat very well because calorimeter strictly means, or calorimetry strictly means measuring heat. And that can be without heat exchange with the environment or with special emphasis on heat exchange with the environment. So both would be good calorimeters depending on what you're looking at. if I want to study how well a little oil lamp transfers heat to my pot with boiling water, or water that I want to boil instead of a stove, then the efficiency of the heat or the oil lamp, whatever, the heat source, then I want to have good heat transfer so that I can measure how well does an oil lamp heat the contents of my calorimeter. So here we have, on the left side of our illustration here, we have a well-insulated walls. We always need a thermometer because for any heat measurement we always need delta T, which is always final minus initial. So if the final temperature is lower than the initial, that will be a negative value, so the temperature or the heat calculated will be of a negative value as well. So it will be exothermic. If the final temperature is higher than the initial, then the process would have been endothermic because the delta T would be positive and so forth. Therefore, delta H would also be positive. You remember the formula, delta H is mass times specific heat times temperature change, and that delta T breaks down into T final minus T initial. If you keep that in mind, we can never go wrong with heat calculations. So you see we have two types of calorimeters. One is very well insulating and one is not insulating at all. Aluminum is a very good heat transfer agent, so therefore you could use a regular beverage, an old Coke can, to do some calorimetric studies of desired heat transfer, let's say of an oil lamp or something of that nature. The calorimeter constant that we sometimes need for calculations is just the specific heat times the mass of the actual calorimeter itself, because there is no such thing as an ideal calorimeter. Nothing is completely insulating. Nothing is completely transmitting in heat. There is no such thing. So therefore, one has to, if one really wants to have exact values, you have to determine the calorimeter constant first by a certain preliminary experiment, and then that calorimeter constant can be used for any calculations that you do in this particular device. So measurement of heat transfer is always the observation of two bodies, let's say A and B. One will always be the heat donor, and the other one will always be the heat acceptor or the receiver. There's always one receiving end and one donation site, so to speak. Now, mathematically, we would have the heat delta H of the calorimeter, which is often considered the calorimeter constant. So the calorimeter also gains heat. Then we have the body of matter that loses the heat, that is the heat donor actually, so it goes from hot to cool. The calorimeter goes from cool to hot, so it absorbs some heat, as I already mentioned, and then the other party is the one that gains the heat. So if you exchange money, the money leaves your hand to the other hand. So there's always an exchange. So you might get poorer and the other person gets richer. So heat always flows from hot to cold, and we learned that with the help of the kinetic molecular theory. It has to do with particle movement. So particles move very much in the hot zone and are very sluggish in the cold zone. So this would be the formula. The sum of all heats is 0. So delta H calorimeter, delta H of the body that loses heat, plus the delta H of the body that gains heat equals 0. And once you have that formula set up, you can solve for any unknown. For instance, delta H of A that loses its heat will have a negative delta H. That means it's an exothermic exchange. And the body that gains heat will have a delta H larger than 0. That means it's absorbing heat from the environment or from the partner. So delta H calorimeter plus mass A times CPA times temperature A change. And then we have B, mass B, specific heat of B, which can be looked up in literature or it can be calculated as an unknown. And the temperature change of B equals 0. You can also calculate, what if I have a hot cup of coffee, and let's say it's too hot to drink, it's 90 degrees or 98 degrees, it would scald your lips, and that's not the desired effect of drinking a nice cup of coffee. So if I put a spoon in here to stir my coffee, what would be the final temperature? You could ask yourself, how much can I drop the temperature of my coffee when I put in a spoon? And here, if you don't have a spoon, I'm using a knitting needle here, which is metal, so it also will do the trick, not as well. But let's say I know the mass of the knitting needle, I know the specific heat of the knitting needle, I know the mass, how much coffee I have in my cup, I know the specific heat of coffee, which is the same as water, by the way, because it's just a dilute solution of some coffee in water. And so the specific heat of water is 4.184 joules per gram per degree centigrade or Kelvin. And this might be, well, if it's aluminum, then that would be 0.9 joules per degree per gram. And if I would mix the two, I could figure out, if I have a thermometer, of course, I always need a thermometer, I can figure out the temperature change from before and after. And remember, once the heat exchange is completed, both my stirring rod, the knitting needle in this case, and the coffee will have the same temperature. So it's then balanced out, so we have an equilibrium of heat. Now we already know about various heat capacities. So let us look now at chemical reactions that produce heat. Before we just did heat transfer due to phase changes or transfer of heat from one body to another, from hot to cold. Now let's look at chemical reactions producing heat. And I will do a little demonstration here for you as well, only in the form of models. Let's say here's my oxygen molecule, here's a hydrogen molecule. And I might need another hydrogen here. I thought I had one, but here's another hydrogen. Okay. Now normally they're both gases and they bump into each other and say, excuse me, and then they have no interaction because the energy is not high enough to make effective collisions. But when I clap my hands or light a match or activate the molecules, then something will happen. There'll be a crash up and they'll stick together for a while, and then the old bonds will be broken and new bonds will form. That means out of the oxygen and the hydrogen, I get two water molecules. And that's a very, very exothermic reaction. If I don't watch out, it will react in the form of an explosion. So you see, water has a high tendency to form. So that's heat of reaction here, as we call that. And it's highly exothermic, and we see here on our slide what happens when hydrogen and oxygen react, if they have enough activation energy. So activation energy can come from a variety of sources, but it has to mean that the molecules make effective collisions so that the bonds can break and new bonds can form. That means if this is successful, we have water as a result. So this is an exothermic reaction. So delta H is smaller than 0. It's a negative value. Now we can control, or let's say visualize this reaction with the help of an energy profile diagram. That means if this is the heat and this is the time, then we start with the reactants that have a certain energy level. And then when we get enough activation, that's going over the hump here, then the reaction can go its course until the products are formed. And if the product's energy level is lower than the reactant's level, then this little difference is called the heat of reaction, or delta H. And this energy difference is called the activation energy. This is only for molecular reactions. Ionic reactions don't need effective collisions. They react in a different fashion. But you can still say if the energy level of the products is lower than the reactants, exothermic. If it's the other way around, we call that endothermic. You see, this reaction's the other way around. That means the level of the products is higher than the level of the reactants. But still, for a molecular reaction, you still have to activate. Otherwise, they're too sluggish. They won't do you the favor. We need effective collisions. That means they have to have enough kinetic energy to do crash-ups, so to speak. So in a way, you can say exothermic means going over the hill, going down the hill, and endothermic means you go up the hill. You have to go against the gradient in a sense, and that is more work than going downhill. Now, just for fun and for the end of our episode, let's look at some interesting things. You all read stories about dragons spewing fire out of their mouths. Now, that's not really that remote of a thought, because they could have eliminated bad breath that contains hydrocarbons, particularly methane, and methane would ignite easily. So that could be a method to deter the enemies or impose on the weaker ones your power. So the combustion of alkanes like methane and oxygen gives oxygen, carbon dioxide and water, and plus a lot of energy. And there is a problem. Some people have a disease. That means they have bad breath like methane. So I hope you don't have that disease. See you next time, and I hope you enjoyed this program.